So we've been using fundamental groups to understand one-dimensional structure, and we have defined the higher dimensional groups by n. Okay. So it looks as if we could just work with them and try to understand higher dimensional structure, except the problem here is they are quite complicated. Now, as I said, the reason they're complicated means that since they're complicated, we can't show they're complicated very easily, so we won't try to do so in this course. But I'll state without proof one of the things which shows how they're rather different from what you might expect. Okay. Now you would expect that pi n of Sn is z, and indeed that is true. Okay, and it's also true that if pi k of Sn is 0 if k is less than n. Okay. So these, and this we have more or less proved. I mean, in the sense we use the same argument which tells you can push off the n skeleton that we used to show. In fact, we proved explicitly the surjectivity from the k skeleton. From that we can show this is true. But what about if k is greater than n? You might think again it vanishes, but in fact pi 3 of S2 is z. Yeah, while we won't prove this, we'll say that generated. We explain what the generator of this map is. And I want to think of this as a map from S3 to S2. Okay, so formally we can think of this, of course, as a map from 0, 1 cubed to S2. But the entire boundary is pinched to a point. So instead we think of it from S3 to S2. And this one thing is, if you see such a map, it becomes plausible. This is non-trivial in any sense, including up to homotopy. The second is it's a really beautiful construction, the Hopf map. That's why I'm describing it. Okay, so let's define f from S3 to S2 as follows. Now what I do is we look at S3 as contained in C2. Okay, so it's the set of pairs of complex numbers z1, z2, such that mod z1 squared plus mod z2 squared is 1. And how about S2? I'll also look at it from a complex analysis viewpoint. I'll look at it as C union infinity. Okay. For those who know projective geometry, you can think of this as CP1, and indeed the construction is more natural in that way. But it's nice enough without that as well. What do? I'll define f of z1, z2 is the quotient z1 by z2. Okay, so that is not that is z2 may be 0, in which case the quotient is infinity. Yeah. So what are the fibers of this map? So fibers are actually all going to be circles. Okay, namely f of z1, z2 is f of z1 prime, z2 prime if and only if there exists alpha, complex number but furthermore in the circle, such that z1 prime, z2 prime is alpha times z1, z2. So the ratio of two numbers is the same if they both differ, if you get one from the other by scaling. And furthermore, because we are looking at unit complex numbers, scaling by an element in the circle. So what we have is S3 is written as a bunch of circles. This one, if you wish, up to infinity, and various ones in between. They're all identified to a point to give you S2. So this is a non-trivial map from pi 3 of S2. Okay, so this is itself a beautiful construction, and it's kind of plausible. This is non-trivial. There is a sketch of an argument that is not trivial. The reason, in very short, is that if I took the inverse image of two fibers, they're going to be circles, but they're not going to be circles sitting far apart from each other. Instead, there'll be circles that are linked like this. One of them is this way, one of them is this way. And it's this linking that can be detected as a Hopf invariant to show that this is non-trivial. Okay, it's one of the ways in which you can show that the map is not homotopically trivial, but that is beyond this course. Okay, instead what we'll do is we'll try to look at an underlying reason why these get so complicated. By the way, here at least it's a nice group called Z. The various other groups are various finite abelian groups. So there's quite a complicated story, and not so easy to describe any of them in any uniform way. So the underlying reason is that there are no combination theorems. I mean by combination theorems, I mean something like Seifert-Van Kampen theorem. And when you see homology, you'll see even better ones, which tell you how given two spaces, if I take a space and write it as a union of two spaces, let's say they're nice and open, this guy is x1 and this guy is x2, then the homotopy groups, including you can define relative versions, are not given in terms of the homotopy groups of the pieces. Okay, so the Seifert-Van Kampen theorem told us, but even there we had a twist. So even that is a homotopy group. We needed path connectivity of the intersection. There's a way around that, and it becomes more complicated there. But for the same reason, it becomes much worse here. Okay, so the reason is the following. Suppose I take a map from S2 into this, and I have x1 and x2 here. The image of that map may look like this. Okay, so if you look at its intersections with x1, you get instead, so let's look at x1 here. So you think of this as a combination of maps. So we broke our loops into loops. So let's try to break our map into maps. So if you think of it as a combination of maps, inside x2, it's the image of not a sphere anymore, but an annulus. And here it's the image of two disks. So if we want to understand maps from spheres, and this was an annulus, it could have any number of holes. If we want to maps from spheres, break. So this is break into maps from planar surfaces. So you can get basically any planar surface. If you try to decompose your map in S2, in S3 it's even more complicated. There's no term equivalent to a planar surface, but the subspaces that you break into can be quite more general than spheres. Okay, you can say planar surface is not so bad, but how about if we rejoin, we'll get maps from all surfaces, all closed surfaces. Why is that? It's kind of clear. So we want a theorem that goes both ways, right? You want to be able to say that any map from the sphere breaks, that conversely given maps that match up, they become maps from the sphere or something equivalent. Okay, so suppose again we had these two, and this time I had an annulus like this, and here I had again an annulus. Their boundaries agree, but then when I go into S2, I'll get a map from the torus into S2. It's no space to draw it, but you can see that when I glue these two annuli together, you get a torus. So you get a map from a torus. So things are more complicated. So essentially, you have to look at maps not from surfaces, but from not from just spheres, but from all surfaces if you want to glue things together. That's because if your sphere is not closed under cutting and pasting. Okay, and while this works for surfaces, you might want to say for higher dimensions you take manifolds, but that's unnecessarily complicated, and it doesn't work well either, perhaps because manifolds are not closed under coning. The cone of a torus is not a manifold. Instead, we can look at something much simpler. Yeah, so instead of looking at globally the domain, we look at pieces of the domain and see how they patch together. And we'll start by doing this in a rather simple context, and in this course we'll stick to rather simple maps and in simple spaces, what's called simplicial homology.